I like big butts and I cannot lie, you other brothers can't deny, that when a girl walks in with an itty-bitty waist and a round thing in your face, you get sprung. Wanna pull up tough cause you notice that butt was stuffed. Deep in the jeans she's wearin', I'm hooked and I can't stop staring. Oh, baby, I wanna get with ya, and take your picture. My homeboys tried to warn me, but that butt you got makes me so horny.
Hey again everyone. Today I'm going to be taking another look at the Coqui TTS project to see where it stands in terms of capability and usability. This is going to be a brief run through of how to fine-tune a single speaker XTTS version 2 model if you find that you aren't getting good results with the base model. And I'll also go through a run of a multi-speaker XTTS version 2 model that you might have mixed results trying to train. The last time I used Coqui was when XTTS version 1 was released. There haven't really been many updates since then, as the company behind the project was shut down. So what does that mean for the open source offerings? Well, it's already showing a few signs of decay. The Coqui framework doesn't depend on too many obscure packages, but when components like NumPy are updated to new major versions, things tend to break. The project has been forked and the new maintainers have done a great job of fixing up some of the bugs. That said, I still find Coqui to be a little bit frustrating. The documentation has improved a lot since its original release, but I feel like the project presented itself as a little too user-friendly for its own good. Many Coqui users were introduced to it through Google Colab. Since the release of Stable Diffusion, Google has clamped down on Colab sessions. Running Coqui trainers on Colab is doable, but you're on your own. If you spend a few minutes to learn the basics of Jupyter Notebooks and how Colab works, you can copy and paste together a Colab script and try this for yourself. Before I go into installing Coqui and training a model, I need to put together a couple datasets to test. There's no hard line in regard to the minimum dataset length, but I'd say that 10 minutes is probably on the edge of what may train well with XTTS, depending on what utterances were included in the dataset and the quality of the recording. Rather than spend time cutting out noises between words and breaths, I'll isolate the speech segments using the Label Sounds tool in Audacity. This will isolate sounds, leaving a slight trail to make sure the sounds are not clipped. Audacity's Label Sounds tool will also overlap samples if they're shorter than the minimum length. Open your track in Audacity and then select the track in the window and hit Ctrl+A to select it all. Then open the Label Sounds dialog. Select a silence threshold at or below the noise floor of your audio track. That's the level of background or recording noise. Set a minimum silence threshold somewhere between the length of a comma pause and a period pause. I generally leave this around 0.35 seconds. The minimum label interval sets the minimum detected segment length. I leave this around 1.5 to 3 seconds. The leading and trailing silence are important, as leaving too long of a head or tail will usually include extra noise, mouth sounds, or other non-speech sounds. Setting this too short will result in unnaturally clipped speech. I think the general rule is to leave 0.1 seconds, but I tend to leave a lot more, and then trim the clips by hand after. I find this captures natural speech much better, and even allows models to spontaneously include breath sounds in longer passages. I tend to leave this about 0.2-0.3 seconds. You can select each sample and hit play to preview the isolated clip. File name for the segments in the box down below, and then select a save destination. If any files have leading or trailing silence that's too long, you can use the a quick wave editor like WaveShop to trim them up. I suggest running the files through FFmpeg to convert them to single-channel 22,050 Hz audio files to be used for training. After the audio files are made, curated, and trimmed, they could be transcribed using the Faster Whisper fork of OpenAI's Whisper. Faster Whisper can't coexist with Coqui TTS due to conflicting requirements, so you'll need to create a separate conda environment for Faster Whisper and install from the master branch. To install Coqui, create a conda environment with Python 3.10, Git, and pip. Install PyTorch with CUDA using the command from the PyTorch installation page. Then clone the fork of Coqui TTS from its GitHub repository. Change to the directory and install it with pip install -e and then in square brackets all dev and docs. Here's a quick Python script that will transcribe a directory of WAV files and write an output file called metadata.csv. This dataset follows the format of the popular open source dataset LJ Speech, and because of that we can use the LJ Speech data loader in the Coqui trainer. The LJ Speech metadata file has 3 columns separated by a pipe character. The first column is the path to the file without the file extension, the next is the transcript, and then the final column is what's normally called the normalized transcript. For the purposes of this video, the last 2 columns are identical. Read through the transcript when it's completed and fix any errors. I suggest retranscribing any triple-digit or greater numbers due to variances in how they're spoken. Similarly, dollar amounts may need to be fixed if there's differences in how they're said. For example, a transcription containing $100 could be $100 or $100 or $100. That transcript would be ambiguous, and those ambiguities may end up being errors and lead to a poor quality model.
$1 million.
Also review punctuation and try to be aware of the speaker's individual style. Place commas and periods in the transcript where the spoken word naturally sounds like they're being placed. Don't place them by default at the end of every sentence in the transcript if they weren't actual pauses in the speech. This will lead to inconsistent, stuttering speech in the fine-tuned model.
He died of dysentery. Give me the watch. I hid this uncomfortable hunk of metal up my ass.
To fine-tune the model, I'll take the basic Coqui XTTS version 2 training recipe and make a few tweaks. The file can be found in the Recipes LJ Speech folder. I have deviated slightly from the original script. First, I've disabled Start with Eval, lowered batch size to 2, and grad accumulation to 32. To configure the dataset on Windows, set the dataset name, path, and metafile path, and language code required. On Windows, you'll need to escape each slash by using double slashes. You won't need this for the initial training run, but to resume a training session, set the XTTS checkpoint to point to a path of a previous fine-tuning run. And again, you'll need to escape it with double slashes if you're on Windows. Set the speaker reference variable to point to an ideal example of the voice you're training. If you're on Windows, you'll need to use a wonky path name with the root directory escaped by double backslashes and the dataset path using single backslashes. I have no idea why this is the case, but any other structure throws an error on my system. For test sentences, I've added a few longer passages to test the voice during training. These sentences can be played back using TensorBoard. Launch TensorBoard with TensorBoard /logdir./run/training. Under load train samples, I've also set eval split to false, and in the trainer config set run eval to false. Do evaluation if you want to, but I don't much care when I'm fine-tuning a well-trained model using a tiny dataset to generate one specific voice. Overall generalization will probably deteriorate, but that's a trade-off I'll make when I'm trying to get a specific voice for a task. You should hear reasonable quality output after a couple hundred steps, and the model's author says that a good fine-tuned speech should be attainable after 1 to 3 epochs. With a small dataset, I find that to really get a good representation of a voice, you'll probably need to go 30 or 50,000 steps, maybe more. It seems to be a long tail problem. The model improves slower as training goes on. It'll appear to be overfitting, with the output repeating at the end of sentences. The repetition will slowly begin to move to the middle of the audio and then to the beginning, and then will kind of merge into the output. Continued training will probably give you a more rich sounding voice. If you can manage to pull the model from training at the right point, before it starts manufacturing new repetitions, that is. The only difference when training a multi-voice model is that you'll need to manually combine your voices into a single dataset, or set up multiple datasets in the script as shown in the Coqui documentation. You'll also need to balance your voices so there is similar quantity of samples of each voice. To generate samples with multiple voices for TensorBoard, duplicate the sample blocks in the trainer script and specify a new reference wave for each speaker. To load the model using the command line or the Python API, rename the checkpoint to model.pth and copy the tokenizer, vocab.json, melstats, and DVA from the original XTTS model files. Those are downloaded to the run directory and saved in the XTTS 2.0 original model files directory. To reduce the file size of the model from 5 GB to around 1.7 GB, you can remove the optimizer states. To do that, use something like this code snippet to load the model and save a slimmed down version. You'll need to rename the file to model.pth to load it with the standard Coqui APIs. Their current community-supported Coqui fork seems to be going well, but I'm sure they could use some donations of time or talent if anyone can help out on the project. It looks like they're hoping to continue the roadmap and are hoping to add support for things like SSML in the future. There are also ongoing efforts to explore how fine-tuning other components of the XTTS model will affect the output. But it seems like simply training the GPT portion does a pretty good job of aligning the output. Selecting the correct representative audio sample is really important though. Different computed latents will alter the output, but this does open up the door for fun things like fusing voices or changing accents by using different samples matched with different voices.
Wouldn't you like to be a pepper too?
What is going on?
I don't know. It must be the print scanner. It must be reading it someplace.
I am not understanding that reference.
Be a pepper too.
That's about all I want to cover in this one. If you found it at all helpful, please leave a comment or a like. I'll probably be working on one more video after this one, expanding on how to use XTTS version 2 fine-tunes in more practical areas. After that, I may step away from the channel for a while. The videos have been getting really poor viewership. YouTube doesn't want to give them impressions in the discovery system anymore. The few of you stumbling across them do it via the search box, and there's little I can do to change that. The videos have reasonable thumbnails, descriptions, closed captions, tags, and even backlinks from GitHub repos where my videos are linked on the front page, and my own site. YouTube just categorically refuses to show the videos I post to the correct audiences during the initial viewing period. That ruins the view metrics, and then the algorithm decides the videos are just spam trash. The only thing that will have an impact now is user interaction, so if you want the channel to stick around, let the algorithm know. Spending 30 hours working on a video that only 30 people watch is sort of silly. I may as well just give you all my phone number and walk you through things personally at that point. Anyways, enough ranting from me. That's all for now. Thanks for watching.
He's gone.
Hey again everyone. I've received a few questions about fine-tuning XTTS version 2 with Hindi speech. The last version of XTTS 2 released was version 2.0.3 I believe, which added support for Hindi, but from the feedback I've received the quality isn't very good. It sounds like it does a poor job voice cloning with Hindi and it misspeaks often.
Malfunction.
Oh, you can talk.
Malfunction. Need input.
Input. That's information.
But that's probably not too much of a problem. Since the tokenizer is already set up for Hindi, there shouldn't be too much of an issue trying to train the GPT model to generate better speech.
Unless $5 million.
I don't speak the language, so I can't really judge the quality of the output that well. But what I can do is share the few fine-tunes that I've done and a few instructions on how you can build some Hindi speech datasets from the open source datasets available, and share the scripts that I've used. I went over fine-tuning XTTS in the last video, which I've linked down in the description. Fine-tuning with Hindi datasets doesn't seem to perform much differently, but there are fewer high-quality Hindi speech datasets available. Coqui TTS supports a few dataset formats out of the box, and I find it easiest to convert my datasets into a format compatible with Coqui TTS rather than writing a new data loader for each different format. For single-speaker datasets, I use the LJ Speech dataset format, and for multi-speaker datasets, I use the VCTK dataset format. The data sources used here are the Mozilla Common Voice version 18 dataset and some of the Indic TTS Hindi database. Most of the conversion is going to be done by hand, with a few clunky scripts that you'll need to tweak for your own use. Here's how I've prepared the Mozilla Common Voice Hindi dataset. The file is downloaded as a gzip tar file. Extract the folder within. There's a tab-separated value file called sentences.tsv that contains the speaker ID, sentence, and file name. Save this Python script and adjust the path names. Set the root path for your dataset, the name of the subdirectory of the new dataset, the path where the validated.tsv file is located, and the root path of the Common Voice dataset. This will sort the dataset into directories with each speaker and save the sentences spoken by each into the speaker directory. It will also save the sentence transcript into an individual .txt file with the same base name as the audio file in the speaker directory. It's using the absolutely stupidest sorting method, and it's ridiculously slow, but it works. Once it's done, you'll still need to resample the audio files, but that can be done quickly with a batch file. Download and install FFmpeg for Windows and add it to your Windows System Path Environment variable. Save this to a batch file and change the sample path to point to the Wave48 silence directory created by the script above. That should give you a VCTK dataset compatible version of the Common Voice Hindi dataset, resampled to 22,050 Hz, and saved in FLAC files renamed with the proper Mic 1 extension so the Coqui trainer handles them properly. The Indic TTS dataset can be converted mostly by hand, but I put together a script to convert the metadata files. Set the input file to the Indic TTS metadata file, and the output file to a new file name that you'd like the metadata file to be saved as. This will be an LJ Speech dataset format compatible metadata file. Extract the Indic TTS male or female dataset and sort the audio files. Delete any files that are too long, so that's files over 13 seconds I believe. I'll treat each of these directories as smaller LJ Speech format datasets. Save this to a batch file and copy and run the batch file in each of the wave directories. Navigate to the newly created out directory and move those wave files back to the original directory, overwriting the original files. Each of your LJ Speech datasets should have a metadata file and a directory of wave files named WAVS. For the Indic TTS dataset, I've used the spoken sentences in the read speech directory, numbers, speaker 1, speaker 2, and bilingual sentences from the additional data subfolder. Since the long files were deleted, you'll need to clean the missing files from each of the LJ Speech format datasets. Use this Python script after changing the input CSV, output CSV, and waves directory to output a metadata file that only points to existing audio files. With these two datasets, you should have something like 16 or 18 hours of speech to train on.
Holy crow, you can read!
Input. More input!
Both datasets could use some cleanup from someone that speaks the language though. Extra silences should be clipped out and poor quality recordings should be removed. The Common Voice dataset is representative of real-world recordings and it's quite noisy. The Indic TTS dataset has a lot of long clips and some that may need to be filtered out. As for training, I followed the same process as in the first video, so I'm not going to repeat that here.
Mix thoroughly. Still lumpy. Marvelous.
What I will do is share this quick script to test the fine-tuned model on a directory of input samples to generate a batch of test sentences. And I'll also share the link to the fine-tuned checkpoints, which you can find down below if you want to try out some of the fine-tunes I've done for this model.
एक बार की बात है, एक शेर रास्ते के किनारे लगे बरगद के पेड़ के नीचे सो रहा था। एक चींटी उसी रास्ते से जा रही थी। वो गलती से शेर के ऊपर चढ़ गई। नींद खराब होने पर शेर तेज दहाड़ते हुए उठा। वो चींटी पर चिल्लाया, तुम्हारी हिम्मत कैसे हुई मुझे परेशान करने की? चींटी मौत के डर से कांपने लगी।
The quality of the speech output isn't going to be perfect. It needs to be trained with cleaner datasets, and it will probably have the problem that most fine-tuned XTTS models do, which is repeating the end of sentences.
अब सिखाई जाती थी तो कहीं यह जात से हटकर एक विशेष पांत भी जाती थी। बनाने वाले लोग कहीं एक जगह बसे मिलते थे तो कहीं घूम कर इस काम को करते थे। I am the very model of a modern major general. I have information vegetable, animal, and mineral. I know the kings of England, and I quote the fights historical, from Marathon to Waterloo, in order categorical.
Sometimes you can work around that by adding or omitting punctuation at the end of sentences, or by adjusting the inference parameters. But after fine-tuning, XTTS seems to do a decent job with Hindi voice cloning. The code snippets for the Python scripts and batch files can be found on the blog post linked in the description. If you found this video helpful, hit the like button or leave a comment. That's the only thing that helps get these videos out into the algorithm, and lately they've been getting very poor viewership. So if you want to see more of these, do the YouTube interaction stuff. That's all for now. Thanks for watching.
Input.